Hello, welcome to another module in this massive open online course. So, we are looking at the properties and analysis of LTI systems. So, today in this module let us look at another aspect, that is the differential equation representation of LTI systems. Okay. So, let us start by looking at differential equation description. Just write it a little smaller. Differential equation description, differential equation description of LTI systems. Okay. And we have seen previously in an example that LTI systems, the input output relationship of an LTI system can be represented by a differential equation. Okay. For instance, correct. So, these systems, so several systems or the input output relationship of several systems can be represented by differential equations. Let us note down that point. Can be represented by a differential equation. Okay. So, we can employ the differential equation, we can employ differential equations to represent the input output relations, and this, so the general structure or the canonical form, the general form of such a representation is that the general form of such a representation is summation m equal to 0 to m am, which is the coefficient, the mth derivative dmyt dtm equals is an mth order differential equation, m equal to 0 to n bm dm xt over dm xt dt. Okay. And it is very clear that xt is the input to system, need not necessarily be an LTI system, and yt is the output. We will see under what conditions this represents an LTI system, and yt is the output of system, output of the system. For instance, a simple example of such a system would be, we have seen this before, I have a current source. Okay. I have an inductor and a resistance. So, I have an inductance L, resistance L, current source described by I of t, the current function is I of t. We have the current through the inductor, which is denoted by IL of t, and current through resistance, which is IR of t. And we have shown, if you denote IT as the input xt to the system, IL of t as the output, that is current through the inductor as the output of the system. We have shown that this can be described by the differential equation L over R DIL t over DIL t dt plus ILT current through the inductor equals the net current of the source. Okay, so this is the differential equation. So this simple circuit which comprises of a current source in parallel with an inductor and resistance, correct, we have shown that this can be represented by a differential equation. Okay. Now since ILT is the output YT and XT IT equals XT, which is the input, I can equivalently write this as LR dyT over dt plus y of t equals xt. So this is the differential equation representation of the input output relationship. Differential equation representation of the input output relation. Okay. Now the solution for this differential equation representation is given by, the solution can be obtained as, or can be, that is, what do we mean by a solution? That is, the solution here simply means the output signal y of t for the given input signal x of t. So, given an input signal x of t, that is signal x of t input to the system, we desire to find the output signal y of t. Okay. So, the solution can be described as y of t, or the output for given input output signal y of t for given input signal x of t. And the solution can be described as, this is the general structure of the solution of this differential equation, that is y of t equals y of p of t plus y of h of t. So, this is basically the output signal can be described as the sum of two signals, y of p of t plus y of h of t. This is termed as y of p of t. This is termed as a particular solution. This is termed as a and this is y of h of t is termed as a homogeneous solution. So, we have two things, we have the particular solution and we have a homogeneous solution. So, any solution y of t, any general solution can be expressed as the solution as the sum of a particular solution and a homogeneous solution. So, y of t any general solution to this differential equation which describes the input output relationship of this LTI system can be represented as the sum of a particular solution and a homogeneous solution. Okay. So, that is what we have over here, and in the homogeneous solution in particular is given as, the homogeneous solution is summation m equal to 0 to m am dy ht divided by dt. So, you take the left hand side, okay, you take the left hand side of this differential equation, okay. So, this is the left hand side. So, you are taking the left hand side, of this differential equation, and you are basically setting the left hand side to 0, okay. So, that describes the homogeneous solution to this differential equation, which gives the input output relationship of the system, okay. So, set this equal to 0, okay, set it equal to 0, and this describes the, this gives the homogeneous solution. This gives the homogeneous solution, okay. And plus we need m auxiliary conditions, plus to solve this we need m auxiliary conditions, also termed as the initial conditions or boundary conditions or so on. M auxiliary conditions are needed to determine the solution. N auxiliary conditions are needed to determine the output signal, N auxiliary conditions are needed to determine the output signal, and these auxiliary conditions are given as, well, these are the auxiliary conditions. These auxiliary conditions are given as basically the values of the output signal or the derivatives of various orders, dy of t divided by d square y of t dt square, so on, dm, the m minus 1th order derivative, dm minus 1 yt dt m minus 1 at some point. So, these have to be given at some point. At some time t naught, let us say, these are the auxiliary conditions. So, these are basically your so we have the various auxiliary conditions which are necessary to determine the solution. These are the values of the signal, output signal y of t, or its various derivatives of various orders, that is dy t dt d square yt dt square, or dm minus 1 yt dt m minus 1, and these have to be specified at some point t naught, okay, so as to uniquely determine, so as to determine the solution for this the output signal yt for this system, okay, described by the differential equation, okay. Now linearity. Now, when can we say the system is linear? Now, how do we? Now, for this system described by the differential equation, when is the system linear? So, we want to answer the question, when is system described by the above differential equation? When is this linear? This is linear if auxiliary conditions are 0, if all the auxiliary, linear if all auxiliary conditions equal to 0. That means the values of dy t dt, yt, dy t dt, d square y dt square, so on dm minus 1 yt dt m minus 1, all these auxiliary conditions are 0 at some point. Okay, only then the system will be linear. If auxiliary conditions, that is, it means to say that the auxiliary conditions have to be 0. Auxiliary conditions have to be 0. Now, further, when can we say, when is the system time invariant? When is the system described by the differential equation above? So, we would like to answer the question, when is the system time invariant? Now, for the system to be time invariant, this system has to be at initial rest. For time invariance, at initial, this is known as the initial rest condition, which basically implies that if xt equal to, for t less than or equal to t naught, then assume yt equal to 0 for t less than or equal to t naught. Okay. And therefore, initial conditions become, that is y of t naught equals dy over dt evaluated at t naught and so on, that is the value of the, that is the output signal at t naught and its various derivatives of various orders until the m minus 1th. Equal to 0. So, these become your initial conditions. So, the system has to, for the system to be time invariant, okay, for the system to be time invariant, correct, that means it has to satisfy the initial rest condition which we have specified over here. Okay. So, if the auxiliary conditions are 0, it becomes linear system. If it is at initial rest, if it satisfies the initial rest condition, then it becomes a time, that is, then the system described by this differential equation becomes a time invariant system. And if it satisfies both, naturally it will be a linear time invariant system, that is, auxiliary conditions are 0 as well as it is at initial rest, it becomes a linear time invariant system. Okay. So, I think that completes our discussion on the differential equation representation of a linear system. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.